In the early 1990s, my group at Harvard was studying catalytic reactions using short laser pulses. The idea was to look at the birth of a molecule. And the molecule that we were studying was carbon dioxide. In every car, there's a catalytic converter that makes sure that any carbon monoxide that is left in the exhaust from the combustion is converted to carbon dioxide. So you have CO for the carbon monoxide reacting with oxygen to form carbon dioxide, which is not as dangerous as carbon monoxide. This is done using a catalytic converter, and the material in the catalytic converter, which is of importance, is platinum. And for many years, we studied this reaction, this oxidation of the carbon monoxide, using very short laser pulses, pulses that are measured in femtosecond or millions of a billionth of a second. Essentially, we took one laser pulse to start the reaction and then another one to measure the presence of carbon monoxide. And by changing the delay between these two laser pulses, we could actually observe the birth of this carbon dioxide molecule. I did that research for many years. It was successful research, but at some point, as you know, with all research, it came time to write for a new research grant and to get money to do something new. However, I had no good ideas. I really, we had still a lot of work to do actually on carbon monoxide and carbon dioxide, but I feared that if I was going to submit yet another proposal for the oxidation of carbon monoxide on platinum, the agency would say, sorry, we've already funded you many, many years. So I mostly wrote the proposal about carbon monoxide on platinum, but I added a little paragraph saying that we would also explore chemical reactions at semiconductor surfaces. Months later, I was sitting in my office and I got a phone call from the program monitor who said, we looked at your proposal and we're thinking of funding you. But we're particularly interested in what you wrote at the end about semiconductors. Could you please specify what you're planning on doing there? Well, I really had written that without giving it much thought, so I promised that I would send in a few paragraphs of details, and I just sent a list of semiconductors that we would look at, and without really specifying the details of any chemical reactions. Anyway, we got the funding, and of course what happened was that we continued to look at the oxidation of carbon monoxide on platinum. 1 year went by, 2 years went by. In the last year, I started to get very nervous because I knew if we were not going to look at some other material, we would never get funding anymore. So I called up my graduate student in the lab and I said, look, we really need to start looking at semiconductors. So he looked around in the lab and he found a box with silicon wafers, which we had used in a totally unrelated project. And he said, silicon, that's a semiconductor. So what kind of gas? Carbon monoxide on silicon is not very interesting. So he looked in the cabinet where we kept our gases, and he found a cylinder that contained sulfur hexafluoride, SF6. He saw SF6, and he especially noted the F-fluorine, which is used as an etchant in the semiconductor industry to etch silicon. So he thought, maybe that's an interesting reaction. What he didn't know was that I had used the sulfur hexafluoride when I was a postdoc here many, many years ago, and that it is an incredibly stable molecule. In any case, he put the silicon in a chamber, pumped out the air, put in sulfur hexafluoride, focused the laser beam on the silicon, saw a spark at the surface of the silicon, and then after raster scanned the silicon surface, and then after the experiment was done, he noticed that the silicon surface had turned black, blacker than black velvet. So he called me, he said, it turned black. I said, how can it turn black? I said, I don't know, come and look. So I came to the lab and we looked, and indeed it looked black, blacker than black. Silicon normally looks like a mirror when it's polished. Not quite like a mirror because it absorbs some light, but it reflects, it looks metallic. Anyway, so we put the black silicon under the microscope, and it still looked black. And then we went to the electron microscope, and we saw that the surface of the silicon, which is normally completely smooth, had this forest of spikes, like a forest of conical spikes. That was the first big surprise. I mean, how did that happen? And then we started measuring the properties of that material, and we fell from one surprise into the other. It turned out that it was not only black in the visible, it was black in the infrared. Now, silicon normally is transparent in the infrared. Glass, which we use for our windows, is transparent in the visible, which is why we use it as windows. Glass is silicon oxide, so it's oxidized silicon. Silicon is not like glass, but it's transparent too in a different regime of the spectrum, namely in the infrared. So even though when we look at it with our eyes, the silicon doesn't look transparent, if you take an infrared viewer, you can look straight through the silicon the same way you look through a window. Now, the fact that it had become black in the infrared meant that something truly special had happened, namely that we actually changed the electronic properties of the material. It took a long time before we discovered what it was. What it was basically that the interaction with the laser pulse puts in a large amount of sulfur, embeds basically the sulfur inside the silicon. So not only does the surface get rough, in addition to that, the silicon itself changes composition to almost an alloy between sulfur and silicon. And the sulfur changes the optoelectronic properties of the silicon. Now, roughly at the time that we discovered that, the Department of Energy wrote a call for proposals that asked for groups to find ways to extend the sensitivity of silicon into the infrared. Any camera, any light detection is currently done in the visible is done with silicon. So for example, the CCD or the CMOS cameras that you buy, the small cameras, the larger cameras, in the chip, it's silicon. It only works in the visible, not in the infrared. If you want to detect in the infrared, you need to use another material. Well, I wrote that call and I thought, this is exactly written for us. Let's write a grant. So I wrote a grant, a proposal, and I asked for a lot of money. I thought I'll just take a risk. And at that point, I didn't know whether it was better than black hair or black plastic or charcoal. I only knew that it absorbed the light. In order to detect light, you need to take the photon and turn it into an electronic signal, something that hair or plastic or charcoal doesn't do. Anyway, within 3 months, I got a call from the Department of Energy saying that we were going to get funded. And I said, how much? I said, the full amount. So I said, oh boy, now I better show that it actually works. So I hired a graduate student to work on this project, who came from the University of Michigan to Harvard. I gave him the project. Within 1 year, we had a prototype that was a silicon-based detector that extended the absorption all the way past the edge, the band edge of silicon into the near infrared. A few years later, that graduate student graduated, and he and I founded a company, and I'm really excited to report right now that there are imagers available that are very similar to the imagers in camera that work not only in the visible, but also in the IR. Now, as we split off this detection to a company, my group became interested in understanding better the process. What is the physics behind it? How does the sulfur get incorporated? Is it sulfur or is it other materials that are important? It turns out that the sulfur is actually very important. We were very, very lucky, or my graduate students years ago was very, very lucky to actually select SF6. He selected it for the fluorine, but it turned out that the sulfur was actually crucial for determining the optoelectronic properties. Another application for silicon and light detection concerns photovoltaics and the conversion of solar energy into electrical energy. We had shown that we could convert light energy into a signal that can be used for detection. Of course, another big application that is really very important right now is, can we actually use this as a photovoltaic cell, as a cell that actually extracts energy from the solar spectrum? The solar spectrum has a significant fraction of energy in the infrared. A normal silicon cell only takes a portion of that energy, because only the portion of the energy that's in the visible part of the solar spectrum, not the infrared part. By also taking the infrared part, you could much more efficiently convert solar energy into electricity. So far, that goal has eluded us. We've been able to increase the efficiency of solar cells somewhat, but we're certainly nowhere near the potential promise of converting both the visible and the IR. We're still doing research, but there are significant obstacles ahead. So silicon is used in two ways with respect to light. One is for the detection of light, such as in a camera or a cell or whatever. And the other is for the generation of energy. Unfortunately, materials that are good photodetectors, so for the detection of light, tend to be poor photovoltaic materials. And vice versa. Good photovoltaic materials tend to be poor detectors. Right now, we've shown that black silicon is very good for photodetection, which, if you base this on common experience and common wisdom, means that black silicon is not that great a photovoltaic material. And so far, it appears that the experiments indeed show that. Of course, there are two things with black silicon. One is the fact that it has this rough surface, which makes it dark and invisible and creates more absorption. That helps. That helps significantly, and that increases the absorption of silicon photocells significantly. In fact, the photovoltaic industry uses a number of different mechanisms to artificially roughen up the surface of silicon that tend to be more costly than our very simple laser scanning. So there's a good reason for doing that. But actually exploiting the dopant, the sulfur that is in the silicon, and this intermediate band that is formed between the valence band and the conduction band in the material is less obvious. And finding ways of extracting the energy is something that none of the groups that are currently working in this area have been able to accomplish. That doesn't mean it can't be done. I know from my experience that there are always surprises lurking around the corner. You have to give yourself an opportunity to find them. So we're continuing to explore this interesting area.